nutrient biogeochemistry are often discussed together. So I won't go into much detail on these detailed figures, other than to say they're in the proposal, the FCE 3 proposal. Do y'all have access to that proposal document? Excellent. So if you haven't looked at that, look at it. It shows obviously the greater Everglades watershed, which we're all familiar with, and the transects, of which Bill talked about, and I will talk today about SRS and TSPH in terms of nitrogen and phosphorus long-term data. But one of the things to keep in mind, in one of Ross's comment about integrating what we understand about carbon and nutrient dynamics with food webs or trophic aspects, carbon is coming into the system through plant productivity, and it's staying in the system, as Bill said, as it's accumulating and peaked. But a lot of the process rates that determine whether it is accumulating or mobilizing have to do with microbial activities. So the work that I'm going to talk about today is trying to set a broader landscape context for the LTR in terms of what do we know about the drivers, what do we know about the nutrient dynamics in the landscape, and what do we know about how those nutrient dynamics may affect carbon process rates, driven mostly by microbes. And when I say carbon process rates, I'm focusing today on respiration and decomposition of organic matter. So we know that was then, this is now. We have a highly altered system. Despite the connectivity that exists, and we have a chapter in a FCE synthesis book on connectivity that Bill and I and Jen Hager, co-author, leads on with several others. But we know that the connectivity in this historic Everglades is much different than the modern connectivity. Yet we still have this setup in Sharp River Slough and Taylor Slough that has nice connectivity with the marsh and mangroves and Florida Bay. The impetus of FCE 3 is to understand strongly how sea level rise and freshwater restoration drive source of water, freshwater, marine water, and how that drives biogeochemical processes of carbon. So carbon is the focus of the FCE 3 proposal, and it will be the focus of our midterm review. So how aspects of marine and freshwater influence carbon, mostly focusing on ecatones. So I won't go through this figure, but showing that the hydrologic alterations from historic, current, and hopefully future with the comprehensive Everglades restoration plan. This is how we think restoration will look on the landscape in terms of hydrology. Using the conceptual model from the proposal, different sources of water, fresh water coming in from the marsh, ultimately from Lake Okeechobee, ultimately rain, marine supply coming in from the Gulf, and also coming up from groundwater during the dry season. Mostly we see that in Taylor Slough. So the concept of FCE 3 is that we have these global drivers such as climate, and they're occurring both in terms of pulse events, storms, droughts, and press events, sea level rise. And we have those operating on regional and global scales. So long-term sea level rise is affecting all coasts. Short-term hurricanes are affecting the Gulf region. And we also have socioeconomic drivers vis-a-vis agriculture, land use, urban. So that sets the template for what's going on in South Florida in general. And then our focus in FCE 3 is on Everglades National Park specifically because of what's going on in SRS and TSPH drainages, as well as the South Florida urban gradient, how humans interact with that and directly influence water availability, and how restoration, humans restoring the Everglades, will directly influence what's going on in the park ultimately. so at the bottom of the watershed. And we've got legacies from the past and scenarios for the future. So this conceptual model builds on the entire proposal. And what you can't see over here, number 1, 2, 3, 4, number 2 is carbon. And I'm going to focus on that as well as Bill did. But the local processes within the park that we're interested in are productivity in the mangrove, the ecotone, and the marine coastal environment. So, did I skip over? Yeah. So the central hypothesis in general, for Biogeochemistry Working Group, I have it here as a question from the proposal. How does the balance of fresh and marine water supply to the oligohaline ecotone influence microbially mediated carbon and nutrient cycling in soils and water? Bill focused mostly on the dissolved and inorganic forms of carbon and sources of carbon throughout that gradient. The red being Taylor Slough, where he mentioned that we have a bump, a productivity bump, and that's associated seasonally with marine water with phosphorus coming in, and we do see a productivity bump where that is coming in what we define as the oligohaline ecotone. But for shark, because it is much more contiguous with the Gulf, we don't see that oligohaline bump. We see more of a gradient from fresh to marine in terms of processes and functions, rates, faster rates.
I have a quick question. Do you think that it's possible also that you don't see that bump because Taylor Slough is so much smaller?
Yes.
And so, you see it in Taylor Slough because it's so much smaller.
Because it's so much smaller. But I think it has a lot more to do with the limestone connectivity coming from groundwater.
Oh, okay.
Yeah, that's a good question. It's also not as directly in line with what's going on in the Gulf. It's kind of it's protected a little bit.
Right.
Yep. So one kind of interesting caveat, so we're talking about these long-term presses and short-term pulses. This is kind of a fun story that when Evelyn and I were at the Science Council meeting at Konza Prairie LTR, this year's focus was on net primary productivity across all LTR sites. And so what each site had to do was come up with the best finding in terms of a unique, unexpected result and the importance of long-term data vis-a-vis the LTR network in terms of finding that. So for us, one of the most interesting issues was the impact of Hurricane Wilma in 2005. So what happens, I'm just going to move through this, but basically how do disturbances, these short-term pulses, like tropical storms, interact with sea level rise and freshwater restoration to modify long-term productivity at the ecotone. So in the mangrove ecotone, when you get this event, what happens past that event in terms of ecosystem productivity? And here, it's this marriage between carbon and phosphorus, or productivity and phosphorus. So Wilma came in and it dumped a bunch of storm sediment from marine source that had a lot of phosphorus in it. And you can see prior to Wilma here, this is the beginning of FCE1, the end of FCE1, beginning of FCE2, and then beyond that we're in FCE3. But in came Hurricane Wilma and it dumped a bunch of sediment up to 4 centimeters, and water total phosphorus jumped up at SRS6. And what happened before, you can see the green is net ecosystem productivity, so that's the tower data. And then the blue is the leaf litter, or leaf and twig litter standing stock in the forest floor at SRS6 near that tower. And so prior to, we had this relationship of seasonal deposition, and then accumulation, and then decomposition. So in the dry season, we start to get it falling down. In the wet season, it starts to decompose. And that drives, even though Bill was asking, well, how is leaf fall productivity a measure? How is leaf fall a measure of productivity? Well, because it stimulates microbial biogeochemical processes that turn over nutrients in the soil that stimulate plant growth. So it is linked. And here what we see, the storm comes in, dumps sediment, blows leaves off of trees. Where'd those leaves go? Did they get buried? Did they get pushed away? But we see that they're gone. Here in 2007, there's low leaf standing stock, but then it jumps back up and productivity comes back. So the system has a capacity to regenerate, but what's interesting is that the average net ecosystem productivity is lower afterwards, and presumably that has something to do with enhanced respiration, soil respiration maybe, but net ecosystem productivity generally reduced, even though it came back pretty quickly. So I'm just going to skip over this particular slide. So what I am trying to do in lead up to the midterm review is just get an up-to-date scope of what's going on along the transect gradients from marsh to mangrove, marsh to bay, in terms of nitrogen and phosphorus, and I'll explain why nitrogen. Oftentimes you don't hear much about nitrogen when I don't even know if it occurred much in our proposal. It's in a few of the slides, but we don't make much measurements of nitrogen because we're a hyper P limited ecosystem, or we're a hyper P limited landscape with ecosystems that are P limited. So what I did here is took the auto sampler data, so they're composited every 3-day grab samples, and their total phosphorus, total nitrogen, and also salinity, but I'm leaving that off for today. And looking at each of the stations along SRS, and then also with Taylor's loop. So what happens here is SRS 1, 2, and 3 at the top, we see that it's pretty low TP. We would expect that. We're getting our phosphorus from marine source, so it's not coming up all the way to the upper reaches of SRS. But after Hurricane Wilma, we do see that bump in late 2005, near 2006, in both SRS 4, 5, and 6. So the impact of Hurricane Wilma on the coast and all that marine phosphorus sediment that was leaching is eventually making its way up towards throughout the oligohaline ecotone. So Bill talked about the mangrove ecotone as an ecotone between the bay and land, but then there's the larger ecotone, the oligohaline ecotone on land that is connecting the marsh to the coast, to the mangrove coast. And so presumably that's where we are seeing these spikes that are coming years later, so up to 6, 7 years after Hurricane Wilma, we're seeing these spikes in P that are greater than what we have seen prior to Wilma. So this is prior to Wilma, after Wilma. So is that causation? We're not sure, but I think it's a good indication.
So what is the idea that's causing the lag increases?
Well, because it's the disturbance of sediment load came in mostly to the coast. Like SRS 6 is where we documented. It also went inland too, but the storm surge coming in is going to drop the heaviest stuff first. And so that marine phosphorus, more phosphorus-rich sediment is going to settle there, dissolve over time, and be pushed in by the tidal exchange in SRS, especially during the dry season when we have less freshwater head. Does that make sense? So that just takes time to work its way up.
And that's on water total phosphorus?
What's that? This is water column total phosphorus, exactly. So then the next step would be to look at pore water, which we do have as well, and compare those total phosphorus with dissolved phosphorus, because the dissolved is what's available biologically for uptake, but most of it is taken up so quickly that we always measure it as total. But so there's more work to do on this, but this is this time series, which is basically trying to assess how discrete points of sampling are influencing the temporal trend over time. So these lines, these time series lines, are created from those discrete sampling points. So nitrogen was, just because I think in terms of N to P ratios often, I wanted to look at the nitrogen in the system. It's super low at the bottom, SRS 4, 5, and 6, but in 1, 2, and 3, we see that there's this spike in nitrogen, total nitrogen again, water column again, and it's occurring in like 2007. So if you go scan the internet for Everglades in 2007, you come across, it was a big drought. And is that drought associated with marsh release of nitrogen? Maybe. And then subsequent to that drought, in 2008, we had the Mustang Fire, which burned off a lot of the vegetation in northeast Shark River Slough area, northeast Everglades, came really close to the urban boundary. And with that fire, you would have then seen, or should have seen, an increase in available phosphorus. Now, are we seeing that in SRS 1, 2, and 3? Maybe not, I don't know. But that would be another thing to investigate. Where did that phosphorus go if it's not detectable in the water column from that fire? Is it taken up right away so you just can't see it? So this is a greater source and concentration, and that is just too much of a discrete release of P that's immediately immobilized. It's hard to say.
Well, right after a fire, there's a lot of plant growth.
Exactly.
So
yeah.
Would it, I mean, maybe it's that.
Exactly. Maybe it's just taken up right away by periphyton and macrophytes.
They're just we have 5
more minutes. Gotcha. So, the trends for total phosphorus in Taylor Slough are I haven't gone down to the total end of the transect with the data. There's no real important reason why that was. It's just kind of hard to find these data in the database. But basically, there is this interannual periodicity of higher P relative to other years, but it's across, it's not seasonal. It's interannual, like it's crossing multiple years. And the pattern seems to be repeated in TSPH 3 and 1, less so in 2, but it's asynchronous, it's not the same.
Might be for the next thing coming up.
I could just turn this around.
Everybody go.
Okay. Okay, so for nitrogen, we do in, at least in TSP2, I think we're seeing an effect of the drought and then leading up that fire that it was occurring. It didn't influence, it didn't have an influence on TSP, but just putting it there for time scale. But also a drought in the upper reaches of Taylor Slough, which appear to have created a spike in nitrogen, at least at some of the sites. And, okay, so going back to this question of how does the balance of fresh water and marine water influence carbon and carbon biogeochemistry in soil and water. One thing that we need to do is first understand our end members. So marsh, mangrove, how are they responding to these differential drivers of different marine and freshwater sources? So one way to do this, work that's been done by Lisa Chambers, Steve Davis, Tiffany Troxler, and others, is just to look at how mangrove peat soils differentially respond to increases in salinity and increases in inundation of water depth. And so in this experiment, they took soil cores, fitted them with gas collars and all sorts of other measurements for looking at the biogeochemistry. And the long and short of this figure is that soil carbon losses increased by 90% with elevated salinity. Nitrogen increased in the form of ammonium by 73% with higher water depth. And phosphorus was released with added salinity. So when they manipulated salinity, they got some release of phosphorus. When they manipulated depth, they got some release of nitrogen and an effect of salinity on carbon loss, but not inundation on carbon loss. So along comes Julio Pichon and Shelby Service, and they decided to look at the same question, but actually add a mangrove to each one of those soil pedons. And then in a manipulation, sort of like Wilma, disturb the plants, remove the leaves, and add phosphorus, and see what happens in terms of various aspects of biogeochemistry and carbon loss, both particulate carbon and gaseous form. And what I'm just showing here are the gas flux measurements that are not completely integrated through time, but we've got 1 through 5 weeks of treatment, phosphorus leaves, phosphorus added, no leaves, so leaves removed, no leaves, or no phosphorus with leaves remaining, and no phosphorus, no leaves, so our controls. And what we see here is that initially, after 2 weeks, we see carbon loss with added phosphorus, but really no effect, this is from the soil, really no effect of soil carbon loss by disturbing the plants in terms of the leaf removal. So what we are seeing out at SRS-6 with reduced NEP is coming from soil respiration or plant respiration. We need to define what's going on. Is it detritus that's being buried in the soil and that's increasing soil respiration, or are the plants actually respiring more? Uncertain. This is my last slide. One thing that we did with help from Sean and Ben and Shelby and Julio and me is we looked at nighttime versus daytime CO2 flux, and not all of the phosphorus leached out the same way in all of these soil pedons. And so what we found actually that was pretty cool was this gradient in P release, and that was showing an interesting trend significantly with daytime soil CO2 flux. And what that suggests is that the phosphorus taken up into the pore water, taken up into the plant tissue that Shelby measured in the mangroves, not taken up into some aspects of the bulk soil and roots, but that phosphorus taken up by periphyton stimulated autotrophic respiration. We get this higher respiration in the day with P, but not really an effect on heterotrophic respiration. So we've got these differential pathways of stimulation of carbon loss. And so for the larger Everglades, I think one of the biggest challenges for us to do will be to integrate these mechanistic studies that we do in small scales, at small areas along the gradient, with what's going on longer in the larger.
Excuse me, what time do you guys finish?
We're done.
Oh, we're done? All right, thank you.
Thank you. This is a busy school. And if anyone have any questions, we can talk afterwards outside. It's a busy school, but everyone's always so nice.
Yeah. Thanks, John.
Sure.